Developing domain-specific algorithms for functions like spatial audio, real-time filtering, or motor control requires massive upfront research and development investments to optimize the microarchitecture. Traditionally, developers monetize this intense effort through non-recurring engineering, or NRE contracts. They sell the algorithm as a custom one-off engineering service. Under the NRE model, revenue is strictly tied to billable labor hours and one-time transaction fees. The total financial upside is permanently capped, regardless of how many consumer devices ultimately ship. An IP licensing model restructures this transaction completely. The algorithm is packaged as a pre-compiled, scalable binary asset, shifting the software from a manual deliverable into a long-term asset. This graph charts both models over production volume. The NRE model hits a hard ceiling. The IP license model dips through initial R&D costs, but as volume scales, revenue rises exponentially. With marginal distribution costs approaching zero, gross margins reach 80 to 90%. Achieving commercial scale requires separating intellectual value creation from manual engineering labor. While highly profitable for developers, a successful IP strategy must also solve a core problem for the original equipment manufacturers licensing the technology. Developing complex DSP algorithms in-house carries severe execution risk and delays. Licensing a pre-built, optimized binary converts that execution risk into a variable cost and sharply accelerates the manufacturer's time to market. When these algorithms are integrated into standard runtime frameworks, system integrators build dependencies on specific tuning interfaces and APIs. This technical retention creates high switching costs and secures adoption in future product generations. Capturing this recurring value requires solving intertwined challenges, structuring multi-layered financial models, securing the physical hardware, and navigating specific corporate cultural norms. A viable, scalable IP strategy must be built from first principles across all three of these foundational layers. A single flat price point fails to align the incentives of a licensor and a hardware manufacturer over a multi-year product lifecycle. This diagram illustrates a multi-layered financial stack. The foundation consists of NRE fees to cover custom integration work and an initial license fee granting access to the development kits and binaries. Above that sits the growth engine, running unit royalties. This is a recurring fee tied directly to every firmware-equipped end device the manufacturer ships. To incentivize mass production, these running royalties use volume banding. As production metrics increase, the per-unit royalty cost decreases down to a negotiated floor. The structure is capped with minimum annual guarantees and ongoing support fees, ensuring the licensor maintains predictable recurring revenue regardless of market fluctuations. This specific stack covers the licensor's immediate engineering costs while giving the OEM an affordable path to scale mass production. The multi-tiered contract perfectly aligns the long-term financial success of the algorithm creator and the hardware manufacturer. Deploying this financial stack requires careful calibration when negotiating within the Japanese market. Western tech firms often demand aggressive upfront pre-buy royalties. In Japanese boardrooms, asking an OEM to assume large financial liabilities before mass production triggers severe resistance. These demands clash with the Japanese corporate imperatives of kyoso, meaning co-creation, and shinrai, meaning trust. This flow diagram illustrates the optimal contract structure for this market. It prioritizes transparent NRE costs, reasonable initial access fees, and highly frictionless running royalties as the product reaches scale. Building consensus, or nemawashi, requires minimizing the OEM's upfront risk while prioritizing long-term shared commercial success. But a legal contract is only as strong as its technical enforcement. Embedded firmware operates in a harsh physical reality. A compiled binary must leave the security of an R&D lab and travel to overseas third-party contract manufacturers for mass deployment. This threat model diagram highlights three immediate physical vulnerabilities in a zero-trust environment: binary extraction, reverse engineering, and unauthorized overproduction by the factory itself. Non-disclosure agreements cannot physically stop a rogue factory floor from flashing your proprietary algorithm onto thousands of unlogged cloned devices. To enforce a sophisticated financial contract, the intellectual property must be shielded by an incorruptible physical barrier. This barrier is established through a hardware root of trust, a mechanism that cryptographically locks the software directly to the individual silicon chip. The first layer of defense against cloning is the physical unclonable function, or PUF. PUF utilizes the microscopic, uncontrollable physical variations that occur during silicon manufacturing to generate a unique, non-replicable digital fingerprint for every single chip. At boot time, the algorithm dynamically derives its decryption key exclusively from this exact PUF fingerprint. If a malicious actor copies the binary to unauthenticated silicon, the new chip's PUF response fails to derive the correct key, and the software refuses to run. The second layer of defense, Secure Firmware Install, or SFI, is designed to prevent factory overproduction. Using SFI, the algorithm is delivered to the contract manufacturer completely encrypted, rendering the code entirely useless to local factory workers. The target processor's on-chip secure engine establishes a direct, encrypted key exchange tunnel with a remote authentication server, completely bypassing local factory systems. The binary is only decrypted and written to the internal flash memory after the external server verifies the licensing rights for that specific piece of silicon. Together, PUF and SFI physically guarantee that every instance of the algorithm running in the wild corresponds to a paid, licensed unit. With the physical architecture secure, one operational hurdle remains: verifying accurate royalty reporting from OEMs without damaging the business partnership. Standard compliance practices, such as sudden, aggressive accounting audits, violate the principle of Shinrai. Treating a partner with open suspicion can permanently fracture corporate alliances in Japan. The secure firmware install process provides a technological resolution. The provisioning server inherently generates objective, automated deployment logs for every authenticated chip. This split comparison chart shows how relying on automated server logs as the verification tool removes human friction and suspicion from the audit process entirely. Technological enforcement doesn't replace business-to-business trust. It protects it by guaranteeing total transparency without confrontation. Transitioning to a scalable DSP licensing model requires a complete shift in business architecture. Success rests on three interconnected pillars: a multi-layered financial contract, strict physical hardware security, and culturally aligned governance. These elements form a closed-loop system where intellectual property is simultaneously protected, scaled, and safely monetized. Maintaining this system demands strict internal hygiene, requiring continuous software composition analysis tools to ensure open-source GPL contamination does not void your commercial IP ownership. By mastering this unified architecture, deep tech developers strip away the limitations of manual engineering and transform high-risk research into scalable, highly profitable digital assets.